In this video, we are going to use RayLab to see how beams of light refract as they go through different materials. So we'll start by creating a new model, and let's set some of the properties of our beam. We're going to reduce fan rays to 1, increase number of source points to 20, and change our wavelength to 730, which is red. Now I'm going to add a lens, and to simplify the discussion, we're going to make this lens flat by reducing the power to 0. And let's make our beam a little narrower by reducing this radius to 10. And let's make this glass material a little thicker. Now we can see what happens as you rotate the plate of glass. When the beam enters, it gets deflected downward, and then when it leaves, it deflects back in the opposite direction, so it's moving in the same direction as before. So let's reset the angle of our glass and go back to options and turn on the feature for displaying wavefronts. I can move this all the way back. The application is now drawing wavefronts every 5th wavelength of the beam. As we move these wavefronts forward, we can see that once they enter the glass, they get closer together. That's because light travels slower inside a material with higher index, and so it has the effect of bunching the wavefronts closer. And then as we keep going forward and we leave the glass, the beam spreads back up and the wavefronts get spread out again. Now let's turn our material and look at what happens when the beam approaches the surface at an angle. In this case, the bottom of the beam is reaching the glass first and it's slowing down, while the top of the beam is still going at the original speed, and so it's getting ahead of the bottom. As a result, the entire wavefront is tilting downward. And so when the whole beam is inside the glass, it's now traveling in a new direction, which is sloped downward relative to the original direction. And when it reaches the second surface, again the bottom is reaching first and it's speeding back up, while the top of the wavefront is still inside the glass, and so it's traveling more slowly. As a result, the bottom gets ahead and the entire beam straightens back out and is parallel to its original direction, even though it's slightly shifted. Now let's look at what would happen if instead of a parallel plate, we were going through a prism. And let's unlock this so we can move it off axis a little. In this case, again, as we go through the first surface, we're tilting downward. But as we approach the second surface, now the top of the beam is reaching the surface first and speeding back up. And the result is that the beam tilts down again, and now it's at a much more oblique angle. The amount by which a beam of light refracts as it passes through a surface can be calculated mathematically using Snell's law. Snell's law relates the incidence angle between the ray and the surface normal to the exit angle between the ray and the surface normal. And as you can see, those angles are proportional to the index of refraction of the material before the surface and after the surface. As a result, if you're going from a low index material to a high index material, the ray bends towards the normal. And as you go from the high index material to the low index material, the ray bends away from the normal. You can visualize this in RayLab by going to options and turning on the ray refraction report. And as you can see, you have to reduce the number of rays. Let's go all the way down to 1. And let's get rid of this wavefront option. So now the application is showing the surface normals where the ray hits any of the surfaces. And in the report, we can see the index of refraction before the surface and after the surface, as well as the angle of incidence and the angle of the output. So on surface 1 here, you can see that we are going from index of 1 to index of 1.5, and the input angle was 19.4 degrees and the output angle was 12.7. And you can see those numbers for all of the different surfaces that the ray goes through, and you can verify that these correspond to the values that you would get by using Snell's law. Next, let's rotate our prism. I can rotate it so that the output angle gets closer and closer to 90. Once it reaches 90, we've reached the critical condition. Beyond 90, it is no longer possible for the ray to refract through the surface. You can see this by plugging in the input angle and the indices of refraction into Snell's law and seeing that it is not possible to calculate a value for the exit angle. When this happens, the ray reflects instead of refracting. This is called total internal reflection, and it can happen when you're going from a high index material to low index material and your input angle is high enough that it is not possible for you to calculate an output angle. Finally, we want to see how different wavelengths behave as they refract. So let's go ahead and increase the number of wavelengths to 2, and let's set lambda 1 to 420, which is blue. And let's rotate this prism so I can get in refraction again. To get rid of some of the clutter, let's delete that first element. And now you can see that the different wavelengths are refracting by different amounts. And we can explain this by looking at the report. At 420 nanometers, which is the blue ray, the index of the glass is 1.528. But at 730 nanometers, which is red, the index of the glass is 1.512. This difference in index of refraction for different wavelengths is what causes the different colored rays to refract by different amounts. This phenomenon is called dispersion, and it's the reason that the prism splits a beam of light into a rainbow. And you can see this by going ahead and adding a few more wavelengths and seeing the rainbow effect appear in the diagram.